Hey everyone, today we're going to cover linked lists for your second exam. I guess that's probably next Friday, so that's going to be the 31st. We're going to go over linked lists as a whole in this presentation, but towards the end, and I will bookmark that in this video, there are some specific stuff. It's all important to know for your exam, but towards the end, there's some specific information I would say sums up what you should really understand for your exam. So we're going to go over doubly linked lists, singly linked lists, operations like insert, erase, copy and move, various constructors. And so we'll just kind of keep working. To start off, we're going to cover doubly linked lists. Actually, hold on. I'm going to set a timer. I want to make this video kind of brief. I know it's annoying when you see like a 30-minute, when you see a 2-hour video and they really think you're about to watch that whole 2-hour video. I mean, some of you guys are troopers like that, but hey, I'm just saying, I don't be doing all that. Anyways, doubly linked lists, what we use in our PA for, or I think it was for, we had sentinel values, which means our head and tail actually existed on the stack and pointed towards objects or nodes that existed on the heap, right? So for the stack, we have node head initialized as this, and note that there's not a pointer. I think I can actually draw. Let me try this. Yeah, okay, let's go. We notice here we kind of have this this pointer symbol to represent that we are going to create a node 1 on the heap. This would be equal new node, but I didn't put that. But on the stack, it's important to note that we are not going to do that for the head and tail. And when we're dereferencing those, it's different, right? Because I mean, we're not going to dereference head, right? Head is on the stack. We'll just say if we want the memory address, or if we wanted to set a pointer to head, we would have to use an ampersand, right? So I wonder if I can actually make this. Oh, cool, I can. All right, yeah. So moving on to the next slide. I guess I should probably get rid of the whatever I've annotated. All right. Yeah, so this is just going to be an erase process that we have here. If we were to start at a linked list of 2, 7, 9 with a head as head and tail as tail, we'll look for 7. That's our goal here. So we'll start at 2. And we'll traverse, we'll find 7, we'll locate it, and then we'll let our next pointer from the previous node go to 9, and our 9 previous go to 2. But it's important that we store 7 before we do this, and that way we can delete it. Otherwise, we will have a dangling pointer and no way to access and delete it, which will be a memory leak. These are just kind of general things to go through it. You can just look through these slides. There's plenty of review notes and links to other slides. There's a good old review. I'll actually pull it up right here. There's an old test review from the last semester, I believe. It's really good to look at. I referenced some of the material from that and changed it just a little bit. But we'll go back into insertion now. Yeah, insertion, we're going to be inserting 7, the one we actually just removed. So we're going to go ahead and look for where we're going to put 7. Say 2, we want to insert it here. In our PA, we had a location to insert, but here we're going to find it. We're going to let our next from 2 point to, or I guess we're going to do previous first. Yeah, 9's previous is going to point to 7. And then 2's next is going to point to 7. But we're not done here. We still need to rearrange 7's previous to 2 and 7's next to 9. And that is all, everything we're doing here, even this erase, that's all technically an O of 1 operation. Because if it looks, we're making 4 main steps here, 2 next, 2 previous, and then 7 previous, 7 next. That is considered an all of 1 operation for insertion and erase, removing or erasing elements. So that's typically one of the things people consider as a benefit of using a linked list. All right, moving on to a copy constructor, we see that we have a goal to copy the values of a other list, and that's the parameter for our programming assignment. It was just list ampersand other, maybe const, I don't remember. And our list should be empty. We assume it is. And from there, we're going to iterate through or loop through the other list. And if we have our pushback working properly, we should be able to, within that for loop and using an iterator, effectively just push back that iterator, and that will create a deep copy of that list so that all the values aren't going to like point to the other list, right? They're new, unique, not unique, they contain the same values, but new memory is what I'm trying to say, right? They just replicate the same value, different memory though. In this loop, and you should go through and look at your PA, I would say that for your copy constructor, your copy assignment operator, your move assignment operator, and your move constructor. Go through and understand, like, maybe not line by line, but as a general statement, how would you construct these and what is the time complexity of them, right? So for a copy constructor, we've got O of other size or O of n as we loop through all the elements in this for loop up here to the other list. I wonder if I can actually, wish there was like a pointer or something. Spotlight. I see Sophia using this sometimes. I don't know how to do it though. Spotlight. Oh, okay, I got it. Let's go. All right, yeah, now it's red. Let's go. Okay, moving on to the next slide. Copy move constructor. Very similar. I just did all that and then I got rid of it. All right, moving on to the next thing, right? How do I, I'm actually bugging right now. I want this to go away. We'll just put it there. Okay. For our copy, our move constructor, we will rearrange the pointers of the other list to point to our list. So think of it as we have our list. It just has a head and tail. It's empty. And we have another list. Everything's full, might be populated with however many values. Could be another empty list technically. We're going to basically, I think of a move as stealing. We're going to steal that other list, essentially. At least that's how I see it. However that works in your head. But we're going to say our head. Currently, the other head next is some value. We're going to say our head points to that value, and then the other head does not point to that, right? So the first thing we'll do is head next of our list should point to the first element of the other. Tail previous should point to the last of other. After we've done those two, I kind of think of it as pairs of things we're doing. We'll go to the previous node of the first element of the other list, and that should equal our head. The last element of the other list should then equal our tail, right? Or rather the next node to it, right? So if we have, I guess, other list should equal our tail. Yeah, this is essentially just meaning that the last element's next node should point to our tail, not the other tail anymore. After we're done with that, we have stolen the other linked list. So the other linked list now needs to be empty, right? It has nothing. So we're going to make it point to the tail as we typically see with other.head equals other.tail and other.tail equals other.head. We'll let our size be whatever other size was, and the other size should now be 0 as it is empty. Understand what the time complexity of this is, right? How does it compare to a copy constructor? Kind of leave this there. You can think about it, and then I'll show the answer. Okay, yeah. So because we're just rearranging pointers, it would be an O of 1 operation for our copy move constructor, which is very efficient compared to our O of n and very useful. If you think about insertion and this, like I said, these are all O of 1 operations. It's very efficient for us to use a copy move constructor in this context. We'll move on to copy assignment operators, I guess, here. We're making 7 minutes. Okay, I'm making good time. Yeah, we have 4 main goals, right? And refer to your code, like I said, and I'll say it, I'll probably keep saying it for the rest of this presentation, but first, the important part is we need to guarantee our list is not equal to the other list. So if dereference to this is not equal to other, if I recall correctly, we can continue with these codes. You can kind of imagine this as an indentation, right? If this is true, then we go through with this. Well, we return this no matter what, dereference this. But these two are within this, like an if statement bracket. We should clear our current list, and we'll cover why we do that. We should loop through the other list. And again, as we did kind of here, we should create a deep copy. Okay, we're going to use pushback, or that's probably the best way I would do it, unless you want to write some really long thing with iterators. It would essentially just be your pushback. So just try to make it as simple as you can. It's a lot easier to remember these 4 steps than it is to try to look at our code, like 12 lines, however many lines, maybe 7 or 8 lines, and then try to memorize every line. Just understand this. After this, we should return our list. And it's important that this is outside of our check to see if they're equal, because we're going to have to return something no matter what, right? It's non-void. This is all of max size, max. So when I say max, I mean, this is big O, like the O notation of this copy assignment operator is considered to be the larger of size and other dot size, which is going to be linear. The reason it is that is because we have our clear, which we'll talk about here in a minute. Yeah, going back to why we clear before our loop, we're actually just pushing back the elements of other. The problem is, what if our list that we have when we set it equal to something else isn't empty? And a lot of the time it isn't, right? Why do we clear before we do our pushback loop? Because if we don't clear, right, and we'll talk about the clear function later, then we are going to just have a bunch of values that are in our list and unaccounted for. And the reason it's the bigger of our current size and the other size is because of that clear function. Because our clear function is O of n, we can't say for, or sorry, it's O of size, which is O of n. We can't say for sure that the size of our current linked list is less than the size of the other. So technically we want to be accurate and say that it is big O of the bigger one, right? So maybe our list is like 500 elements long, and maybe the other list is 10 elements long. Well, which one takes longer, right? Let's say you have to do both. You have to clear 500 elements and delete 500 nodes, and you have to push back 10 nodes. Which one takes longer? It's going to be the 500 nodes. So in that case, it would be O of max size, which is this. But at the end of the day, it's still going to be a linear traversal for clear and for our pushback loop, which creates a deep copy. So we'll consider it O of n. Okay, our move assignment operator. Now this is kind of one of those things where I'm going to keep going back because it really is that similar. Our move assignment operator is going to check to see if it's equal, just as our other assignment operator does. And otherwise, or I guess the formation of this one is different. Yeah. So if our list is equal to it, we should do nothing and return this, which is essentially what we have here. It's just written a little differently. If it's different, we need to clear it, right? And our move, well, we need to clear it as we did in this assignment operator is what I should probably say. Same reason, right? And that clear will be O of n. And we need to rearrange pointers just as we did in the move constructor. And that's what I was trying to get to right here. This copy move constructor, it's these same lines. If you can understand and visualize, like these, memorizing these might not make sense, but if you think of what steps do I need to take to properly update, and you might even draw like a linked list with a head, a node, and then a tail, and all pointers, so 6 pointers, and you might draw just a head and a tail below it, and you might say, what do I need to do? This head's connected to this tail's connected to it. What do I need to do to connect this to this list above, which is the other in this case? And what do I need to do to other after I've connected it to this to make it so it's empty again? And if you can understand that, if you do it part by part, you will end up writing these lines. So it shouldn't be too difficult if you think of it intuitively like that. All right, why do we check for it to be equal? Why do we clear? What's the time complexity? The reason we check for it to be equal, I just say efficiency. It's very similar to that of our other assignment. Why do we check for it? This bullet point's almost useless. Why would we do all this work if they're just the same, right? And if they point to the same thing on the heap, why do we clear? It's the same reason as before. This version's a little bit more, I guess, nihilistic. If our current list wasn't already empty, we rearrange the pointers of our current list to match with the other's values. What happens to the elements of our current list? Yeah, they're just gone forever, never to be known again. And remember, just as memory leaks and seen through address sanitizer -f sanitize flag in your compile. Okay, the overall complexity of this is going to be O of n, or O of size. And it's not going to be anything like this one where it was like, oh, well, it's O of max size. And the reason for that is because we have a clear that is O of n, and we have a actual move of rearranging pointers that is O of 1. So between O of n, or O of size, and O of 1, the larger one or slower one is going to be O of size. There is no comparison. All right, for our destructor and clear, and the reason I put clear is our destructor has the same effect as clear, because we use clear in some other functions. We call clear in our destructor. You didn't have to, I don't think. Maybe, I think some people's clear actually called the destructor, and their destructor was their clear code. Yeah, but this is just a pretty simple one-liner. I mean, there's not really much to say about it. Like, it's just a little for loop. I'm sure most of you guys were able to do it in one. This might have been a little inefficient, but yeah. Anyways, moving on. Okay, no, I'm just kidding. I'm just so funny, so I decided to put this as a joke. Yeah, this is technically, it does work, right? And if you think about it, go look into what erase returns. And you might think, why did our erase return that? It's so that we can do stuff like this. But a general set of code, which most of you wrote, because I doubt any of you wrote iterator and erase and then clear, probably would have been the exact opposite way, clear first. Some readable code, which all of you wrote, is the same as what you did in 121. You start at your head. In this case, you could do tail recursion. You could start at the tail because it's doubly linked. And you just have these 6 lines, basically. Current equals head, next equals current next. You delete the current node, update it with the next, update the next with the next of that next, and keep decrementing size if you would like. You could just set size to 0 at the end. I personally like to do size minus minus in my code just because, like, I mean, I guess I know if my size is not 0, that means somewhere I went wrong, right? Maybe I forgot to delete something or deleted one thing too many. But I guess that would just be an error that would be checked on its own with the test cases. An intuitive approach I kind of put, because I was talking before about how important it is to kind of memorize and understand how you would write something with an STD or standard library list class. I would say intuitively, it's a lot easier to remember something like this right here, which I put as a joke before, but actually, I mean, logically speaking, if I ask you to write a clear, you can use everything, obviously, except for the clear of standard library list. I mean, you could use iterators, you can use erase. It's a lot easier to remember a proper way to do it than, you know, something that is exactly right. But something like this isn't so bad, but I'm just very lazy. So as far as readability, this is pretty much this, right? But this is a for loop, this is just a while loop. And I'll explain this. There's questions here, I'll explain. Yeah, so why is there no iter plus plus? Typically we see in our loop iter plus plus. Well, if you remember, we gave erase a return type, which is an iterator. And I remember some people had wondered, why are we using a return type of an iterator? And why are we even, you know, why is it not just void? Like, why are we not just doing something? Actually, I don't recall if insert is void. I don't know, but why are we, people are asking, why are we using erase as a non-void return type? It's so that we can do things like this, which I mentioned earlier. So we will return the iterator to the node after the element we removed, which means every time we call erase, we can choose to do something like this and store the next node, because it not only, when you type iterator equals erase, not only will it erase iterator, it will return the node next to it, or an iterator to that, right? Which means if we just say iter equals erase iter and we call that n times, we effectively have just made an iter plus plus, right? So there's no iter plus plus whatsoever. It's kind of in our erase in a way. And it also helps avoid iterator invalidation for that exact reason. If we have a for loop and we try to do iter plus plus, things just get kind of weird. The idea of, let's say we tried to return an iterator to the element we just deleted, that it just doesn't work, right? So think about iterator invalidation with regards to that. Is there something missing from this? Yes. Size minus minus. I'm pretty sure most of you guys used size minus minus in your erase function, but I just wanted to make sure that, I guess technically you could include it here, and I didn't want to completely deny the possibility in the case that there's that one person who chose to, not that one person, like I'm putting them out on a limb, but suppose there's someone who did that. Actually, I see something here. It's annoying. I can't believe it's been there the whole time. Okay, yeah, moving on. Okay, yeah, I'm going to talk about big O notation. This is pretty important. Everything I've noted here with 2 asterisks is pretty important in my eyes, and I will bookmark this part of the video. First, we're going to talk about linked list erase. As I said before, it's O of n. The erasure itself, like erasing, is O of 1, as we're just rearranging pointers in a linked list. But the problem is searching for an element at worst is going to be big O of n, right? Because we don't know if the element's the first or the last. Now, I would say it depends, right? What if our linked list happens to be sorted? Then we know certain things like find min, find max, that's O of 1, right? And we know that searching for the max element would be O of 1. So just kind of understand intuitively in your head why erase is O of n. It doesn't take O of n to erase it. It takes O of 1 and O of n to find the element. And like I said here or before, it differs depending on the form of erase call. Like when I say form, I mean there's pop back, pop fronts. I think those are main two we use. And it depends on the linked list type, right? If you have a singly linked list, let's say you have a singly linked list, right? No tail, doesn't matter if you have a tail. Yeah, but let's say you have no tail and you just have a head and it's singly linked. What is the time complexity to call a race? For not a race, sorry, for pop back. It would be O of n, right? Because we have to traverse to the last element and there is no tail and there's no way to go backwards. Let's say there is a tail, it would be O of 1. But there is not a tail in a singly linked list. I suppose it would be specified. Some singly linked lists use a tail. And the same for pop front, you can think of that. Going on to insert, that is O of n again, because it is O of 1 to find or to actually insert the node, which is just rearranging pointers. But to search, it's O of n, right? The same. It's pretty much the same. And that's kind of similar with trees and balancing trees. You'll see that it ends up being searching for the proper place to insert and erase. Like seeking the node can actually be the main reason for these time complexities not just being O of 1. So let's see. Yeah, think again about differs depending on the form of insert called. Like there's push front, push back. If I say to push fronts on a singly linked list, it's just O of 1, right? You're just pushing to the front, you're just adding, right? And if you say push back on a singly linked list with no tail, then obviously it's O of n because you have to travel n elements to get to the last. But if it were the first element, it would be O of 1, and same for push fronts. And I guess you can just play with that in your head, right? It's up to you. If it's a tail, I guess if it's a singly linked list with a tail and no head, then I guess you would have to. Anyways, I'm just talking in my head. This is irrelevant stuff. I wouldn't worry about it. Okay. Copy and move constructors. As I said before, I've went through these. I just wanted to include them here. Our copy is O of other dot size or O of n. Move is O of 1. This is going to be O of max size and other size. The larger of the two, as I said before, for clear. The clear function in our copy assignment is the reason our size is compared to other size here, because it might take longer to clear our current list than it does to actually populate our current list after it's cleared. So we'd have to consider that. Either way, it's still O of n. And I kind of wrote that here. O of size, I mean O of n. Move is O of n for our copy and move assignment operator as opposed to O of 1, because just again, as we have here, we have to clear it. Destructor is going to be O of n, clear. Search is O of n because in the worst case, we're searching for 7 in a linked list of random numbers where only 7 uniquely is at the end of the list. That takes n to traverse. Now, if I ask you to find the length of a list or the total number of elements in a list, it would just be O of 1, right? You might think, oh, it's O of n. I have to keep incrementing, right? If you have a private member, which we do, it is O of 1. Okay, some extra notes I wanted to briefly say. I pretty much already talked about these. Yeah, it is important to understand where the search. Yeah, understand. Yeah, think about singly linked list versus doubly linked list for things. How does that affect our search time? Yeah, this is pretty much it. For a linked list, I provided some examples that'll kind of help, right? Given a standard library list or list structure, how would you go about implementing various data structures? Maybe, I don't know, a queue, a stack, a clear function, things that I said were important to understand how to do as far as concepts here, and how it's easier to understand this than it is this. Just kind of, if you don't really understand how to do that, go ahead and open whatever, include lists, and just try to understand how iterators work with the standard library list class, how we can dereference those iterators, how we can kind of just access nodes. And not every, one thing about a linked list is not every node stores a value of, right? This is template classing, right? And this just kind of goes down here. We don't have to store an integer. So if we dereference an iterator, that just gives us the value that is there, right? But the value isn't always an integer. Maybe it's a struct. Maybe it's a struct that has other things that we need to dereference, which leads me to my next point of understand what every single step of something like this gives me, right? understand that if we put a parentheses around this, it's this, like pointer next is something, and then the next of that dereferenced is this, and so on. Understand how to draw that out. If you were to see some linked list of whatever data type that's templated, be able to understand what everything is. Understand how sentinel nodes are different from our heap constructed nodes, which are the actual value holding nodes of our linked list. And lastly, this is a very important one. Understand the time at which templates are instantiated. Right? They're instantiated at compile time, okay? Anyways, that's pretty much everything for this linked list review. I guess 25 minutes, it's okay. If you made it this far, hey, like I said before, you're a trooper. Go watch the other videos. There's some old slides I talked about earlier. Linked list, there's pretty much everything in here. These are Sophia and some other PTs and TAs. Yeah, exam 2 review from last semester. There will be a doc you'll see with the new material, but a lot of it is heavily similar with some specific changes. So if you want more review, just go look on here. And yeah, like I said, go watch the other PT's material and TA's material. And thanks for watching, guys. Good luck.